Hey everyone! In this video we're going to talk about backtracking. First of all, we're going to understand what backtracking is. Then I'm going to share with you my formula on how to solve almost any backtracking question. And finally, we're going to go through 3 different questions asked by real companies in real tech interviews. So, with that in mind, let's just jump into it. So first of all, what is backtracking? Well, backtracking is an algorithmic approach for solving problems using recursion. In this method, we're going to try all the different possibilities that match the criteria of the question, and then slowly moving towards an answer. If at some point we reach a dead end, we need to backtrack back to the last step we took and try a different path. You can think of it as a maze. In the maze, the goal of the maze is to go out of the other side, right? And you can't walk through walls because you just can't. So what do? You just walk straight and then you reach an intersection and you have a decision to make. You need to choose either to go left, straight, or right. Let's say for this example that you decided to go left, and then you continue walking until you reach another intersection, and you continue this way until you either go out of the maze or you reach a dead end. If you went out of the maze, well, congratulations, you won. But if we reach the dead end, you need to go back to the last intersection you took and then choose a different path from there. So, how do we know that we can use backtracking to solve a coding question? Well, before answering this question, I want you to think about something. Let's say our maze doesn't have an exit. So, what will we do? We will go to the first intersection, decide of a path, go to that path and continue in this way until we reach a dead end, right? And then we're going to backtrack back and then reach another dead end and so on and so forth until we reach all the dead ends in the maze. So, with this analogy in mind, there are 3 different themes of questions that we can use backtracking in. The first one is when we have a clear goal and clear constraints. Let's say, for example, solving a maze or maybe solving a Sudoku board. In the Sudoku problem, we have a clear goal. We need to fill all the blanks, all the blank spots, right? There are really clear constraints. We need 1 through 9 in each block and 1 through 9 in each row or column. So these are really clear constraints. The other type of question, if we're being asked to generate all possibilities of something. The third one is really similar to the second one. We need to generate all the possibilities, but from them we need to decide of the best answer. We will see an example for it later. But just be careful because this might take a long time. So backtracking isn't always the best option, but some questions you can't really do without backtracking. So it's a great tool to keep in your pocket. So now, when we have a clear understanding of what backtracking is and when to use it, I want to share with you my formula on how to solve almost any backtracking question. The formula contains 5 steps. The first one is to create a recursive function. The second one is to think of a base case. The third one is create logic and decisions that will get you closer to the base case. The fourth step is to make a recursive call with the decision that we made on step 3. And the fifth step is to backtrack back. So now let's expand on these. The first one is to create a recursive helper function. Why do we need that? Well, because usually the main function will not have the right parameters for us to solve the question, using backtracking of course. So we need to think of how we're going to implement the backtrack, how we're going to make progress toward the solution and create the right helper function with the right parameters for us to implement our solution. This is step 1. Step 2 is think of a base case. For example, in the maze, we need to think of when we can't continue moving forward. This will happen when we can't go forward, left or right? So when we reach the point where we cannot continue moving towards the solution, usually this will be the base case. The third step is to make a decision to go towards the base case. For example, in our maze, when we reach an intersection, we need to decide either we go left, straight or right. In each possible way, we made the decision to continue forward. The fourth step is the recursive call. In the maze analogy, the recursive call matches the walking part. After we made the decision in the intersection to choose a specific path, the recursive call will make us walk in that path. And then we reach step 5, the backtracking part. So when we did the fourth step, we decided to walk, we can find out that either A, we reach the end and then we need to just exit, and B, is that we reach the dead end. So when we reach the dead end, we meet the second step, right? So we're going to go back, we're going to return back. And then we're going to return to the line after the recursive call. The job of this line is to tell the program, wait, we don't want to go left. We want to go straight to the intersection and make a decision from there. This is the most important part in the backtracking algorithm. So now that we have the formula in mind, I know it still doesn't make a lot of sense. So for that, we have 3 different questions that we're going to do together to try to implement this formula and try to get better at it. So without further ado, let's jump to the first question. This question is called permutations. In this question, we've been given a list of numbers and we need to return all the possible permutations from these numbers. We can see that the question asked us for all the possibilities of something. Sounds a lot like the second type of question, right? Let's look at the first example. We've been given a list with the numbers 1, 2, and 3, and we return all the possible permutations from these numbers. So now, before we jump into the code, let's build a plan on how to solve this question. So how are we going to approach this solution? First of all, we can see in the example that all the permutations need to be stored in one large list. We can notice another thing, that all the permutations are stored in individual lists. What we can do is we can create a list and add to it the numbers in some order. Once this list is with length of 3, we know that we added all the numbers to that list, which means we created a single permutation. So what we need to do is just add it to our answer. Then for the next permutation, we don't have to create another brand new list. We can use the exact same list, but change the order of some of its elements. After we did that, we have a brand new permutation to add to the answer. So now we can already use the formula to predict how the algorithm is going to look. First of all, we're going to decide on a recursive function. Then we're going to write the base case. In this question, the base case will be that our temporary array, the green one, will reach the number of elements that we originally had. When we did that, we know that we created the permutation successfully. So this will be the base case. So if we continue with the formula, we know that right now we need to make some type of logic to walk towards an answer. And how do we do that? Well, we loop over all the elements and then we add them to our temporary array, the green one. After we added a specific number, we're going to make a recursive call. We're going to commit to that decision. This is step number 4. One more important thing that we need to notice is that after we added a specific number to our permutation, we need to remove it from the original list. For example, after we added the number 1, we need to remove it in the next iteration, in the next recursive call, so then we can only add 2 and 3. And in step number 5, we need to backtrack back. And how do we do that? Well, let's run a small example. We're starting with the numbers 1, 2, and 3. Our pointer in our loop will start at the number 1. So we will add the number 1 to our permutation. Then we need to pass the function, the list, without the number 1. So now we're having number 2 and 3. And then in this iteration, we're going to loop through all the numbers, which will be 2 and 3. And then we're going to add 2 to the permutation. And then do step 4 again. And then again run through all the numbers. Then we're going to have only the number 3. We're going to add it to our permutation. And then on the next call, we will reach step 2, the base case, right? Because our permutation is already at the length 3. So at this point, we will add the permutation to our answer and then return back. After we return back, we're going to reach the backtracking part, which will remove the number 3 out of our permutation. Because at this level in the recursion, we have only a single number, we are going to go back another step of the recursion. Then what will happen is that we will go outside of our recursive call and then backtrack out the number 2 from our permutation. So now the permutations contains only the number 1. And then our loop will continue to the number 3 because it was on 2 and now it's 3. And then it's going to add the number 3, and after that we're going to yet again go inside our recursive function. And as you can see on your screen, this is how the permutations are going to be built. And now let's jump into the code and see how are we going to implement this logic. Now is the part that we need to practice the most. Convert our ideas and our intuition into code. First of all, we can see the permutate function receives only the numbers that we start with, but we understood that we need more than that. Now, according to the formula, we need to create a recursive helper function. This function will have the right parameters for us to implement our solution. The parameters that we will need will be the temporary array, the numbers, and the big list. We will call it ans for answer. Then, after we decided on the right parameters, let's continue to the second step of the formula, which will be create the base case. We know that once the temporary array is with length 3, then we need to add the temp into ans, right? This is step 2. Step 3 is create the logic. So we will need to create a for loop that go over all the numbers inside nums. Then we need to add to temp the number in nums in the ith location. This is step 3. In step 4, we need to create a recursive call. But here, notice that we shrink the array and remove the ith element. This is how we walk towards a solution with the decision that we made. And after that, the 5th step is to backtrack. But how do we do that? We just remove the last element added to temp. And with that, that's it. Our solution is ready. The only thing we need to do is return the answer inside the permutate function. And now let's run it. And there you go. You see, it wasn't that bad, right? So now let's continue to the second question. Before we continue to the second question, if you're enjoying the content or you learned something new, please click the subscribe button. It will help the channel a lot and I would really appreciate it. So thank you, and with that out of the way, let's continue to the second question. This question is called word search. In this question, we've been given a grid full of letters, and the word our job is to determine if the word exists in the grid or not. If it does exist, we need to return true. Otherwise, we need to return false. Let's go through the examples. In the first example, we can see that the grid is described by a list of lists. And as you can see, the word really exists in the grid. On the second example, we can really see the word see in the grid. And in the third example, our algorithm needs to determine that this word does not exist in the grid. This question is a bit harder than the last one, but as you'll see soon, it follows the exact same steps that we used in the previous question. So yet again, before we jump into the code, let's build a plan on how to solve this. A good option is to go over all the letters in the grid and see if there's a letter that matches the first letter of our word. If so, we can use another function that will check the next letters in the grid. And this function will tell us if the word exists in the grid or not. So now we can use our formula to visualize how this function will look like. First of all, we need to know what the parameters of the function will be. So we know we need the grid, right? And we know we need the word. But we also need the row and the column of the letter that we found when we ran through all the letters. So we have the right parameters. Now the next step is to think of a base case. And similar to the maze, we have two different options. Either we win and we found all the letters, or we lost and we reach a dead end. So now let's think of how a dead end looks in this question. A dead end in this question have two different options. Number one is when we search for another letter, we went outside of the grid. That's obviously a constraint. We can't do that. The second option is if we reach a letter that doesn't match the letter in our word. So this is also a dead end. But how do we know that the letter that we're in at the moment in the grid matches the correct letter in our word? What we can do is remove the first letter in our word in each recursive call. We can check if the letter that we're in the grid matches the first letter of our word. And also, we can know this way if we won or not, because if the length of the word is 0, we know that we found all the different letters that were originally in the word. So we have our base case. Now, let's go on to the third step, which will be creating a logic to get towards the base case. Before we expand on step 3, I want you to think about something. Let's say the word we're looking for is AAA. When we look through the grid, we found the letter A, and next to it there's another A. What will happen is that we'll go to the A, and then go to the second A. But then we can see for that A, over its side, there's another A, the first A that we went for. So to counter this in our logic, what we can do is to temporarily change the letter that we're standing on in the grid to an empty string. Then we will not meet this edge case, right? Because we will go to the first A, change it to an empty string, then go to the other A, and then we won't go back. So in our logic, we will save the letter that we're standing in and then change it in the grid to an empty string. Then we can jump to step 4. We can walk towards a solution with a recursive call. Our recursive call will be either we go up, right, down, or left. Then we only need to implement step 5, the backtracking part. And how will we do that? We need to remember that we changed the place that we're standing on to an empty string. We need to change it back to the original value it had before we landed on this square. And after running through all the letters in the grid, we either stop the loop because our function found the word. And if the loop continues all the way through, we know that this word doesn't exist in the grid. So now, when we've got this plan, let's jump into the code and implement our solution. So as we said, let's create 2 loops that run through all the rows and the columns of the grid. Then we need to check for 2 things. The first one is if the letter that we're standing on the grid matches the first letter of the word. This will make sure that we won't call our recursive function for nothing. The second thing we need to check is if this letter is really the start of the word. If so, we need to return true, because the word exists. Otherwise, we need to continue in our loop. Now, let's run through the function. Notice that the function receives I, the row, j, the column, the board, and the word. Now, we need to implement the base case. The base case have 2 options, right? We need to check either we found the word or we reached a dead end. So if the length of the word is equals to 0, we need to return true. We did find the word. But if we went outside of the grid, or the letter that we're standing on does not match the first letter of our word, we need to return false. We reach a dead end. Now, for the third step in the formula, we need to create the logic to walk towards the solution. Now, as we said in our plan, we need to temporarily save the value of the letter that we're standing on in the grid and change it to an empty string. Then we jump to step 4. Make a recursive call that walks toward the solution. We either move up, right, down, or left. And now, for the 5th step, we need to backtrack. What we need to do is to change back the value from an empty string back to the value it had before. And the last thing we need to do is to return the answer, because it doesn't help us if we only returning the answer with the base case. We need to return the final answer all the way back through all the recursive calls. And with that, we finish the second question and ready to go to the third. So we finally reached the final question. This question is called find minimum time to finish all jobs. I know this red hard tag looks really intimidating, but I promise you this question will be a piece of cake. We've been given a list full of numbers, and each number represents how much time will it take to finish a job. That was the first argument to the question. The second argument is k, and k is the number of workers we have. So our job is to assign each worker a different job. Each worker can do only one job until he finishes it. After he finishes it, we can assign him another job. So the goal of this question is to ask us what is the best way to split the jobs between the workers to achieve the minimum time for completing all the jobs. In the first example, the jobs array is the numbers 3, 2, and 3. And the number of workers is 3, right? So we can assign the first worker the first job, the second worker the second job, and the third worker the third job. So the maximum time it will take to finish all jobs is 3 hours. But let's say in this example that k equals 2. So we can assign the first worker the first job, which will be 3 hours, the second worker the second job, which will be 2 hours, and then we'll have to wait until the second worker finishes its job. So we need to wait 2 hours, and only then assign him the last job. So the algorithm needs to print out 5 because the first worker had to work 3 hours, and the second worker worked 2 hours. He finishes his job, and then he gets another job that costs 3 hours. So by the end of it, all the jobs will be finished after 5 hours. So for the final time this video, before we jump into the code, let's create a plan on how to solve this. So this question is really similar to the second one. Let's first analyze how we're going to approach this solution. We need to know what is the best way to split the jobs so the maximum working time will be minimal. Our approach will be to generate almost all the possibilities of different arrangements and track the best time. We can also notice that the number k, the number of workers, doesn't really help us a lot. What we can instead do is to create a list with the size of k full of zeros. Each spot in this list will represent one worker. Then, when we want to assign a worker a job, we can just add to this index the length of the job. Then, the maximum working time will be the biggest number inside this list. So, a good way to approach this solution will be to go over all the jobs and assign them to different workers. Whenever we assign all the jobs, we know that this will be the arrangement. Then we need to check what is the maximum number inside this list. So now we can go to the formula and see how the algorithm will look like. First of all, we're going to need a recursive function. This function will receive the jobs list, the list of all the tasks that we need to do. Another list that will represent the arrangement, with each index in that list represent a worker. We need an index that will track the current job we want to assign. And we need k, the number of workers. So that was the first step of the formula. The second step is to think of a base case. Well, what is the base case in our question? So the base case is that our index reached the end of the jobs list. When we reach that, we need to check what is the maximum value in our workers array. We also need a global variable that will track the best time we had so far. And if the arrangement we got is better than the one we had before, we need to change that global variable. So now we have our base case. We can continue to step number 3. Create the logic. Our logic will be to go through all the workers and assign to them the job that our index is currently on. Then we can move to step 4. We need to make a recursive call that will make us go towards the base case. So what we need to do is to increment the index by 1, because the index controls which task we are assigning to our workers. So that was step 4. And finally, step 5, will be to backtrack. We need to subtract from the workers array, with the worker that we're currently on, the value from the jobs array in the current index. And that's it. That's the algorithm. We have minor improvements to do, but that's mostly it. Now, let's jump into the code and finish this question. Alright, so as we said in the plan, we need to make a list with size k full of zeros, because each worker in the beginning doesn't have a job yet. Then we will create our global variable and call it best time. This will be a very large integer. This way we will always optimize it to something less. Now we can create and call our recursive function. When workers will be the list of workers that we're going to assign the jobs to. C will be the index that will track on which job we're in. Jobs will be the list of jobs that we need to do. And K is the size of the workers array. Now to our base case. If C is equals to the length of jobs, we need to update best time to be the minimum between the maximum working time of the workers and the value best time previously had. Then we can continue to the logic. We need to go through all the workers and assign them one at a time the current job that we're in. Then we can jump into step 4. That will be call the helper function. Now with C plus 1 we want to go to the next task. And then we need to backtrack. And we're doing that by subtracting the workers at a place I, the jobs at a place C. Now the only thing that's left is to return the best time. Now let's run this code and see that it does pass the simple tests. But when we try to submit, we will see that time limit exceeded. Why is that? Because when our K is really big, we have a lot of ways to assign the jobs to our workers, and that will take a lot of time. So we can do two things to help the solution be a little bit quicker. The first thing is, let's say for example, we have multiple workers and each one of them has a job that costs, let's say for example, 2 hours. It doesn't matter if we assign the next job to the first guy who has a job of length 2 or the second guy who has a job with the length of 2. What we can do is to make a set that will track all the different jobs that we store in workers. Then, if we already assign this job to a worker with similar time, there is no need to explore this option because we already did that. The other improvement is if we're assigning a job to a worker and this is already bigger than the best time, we don't need to explore this option as well, because there is no way that this option will result in a better time. And if these two checks don't happen, we can add to the set the current time of the worker that we're going to assign the job to. And now let's submit, and there you have it. We just finished a hard backtracking question. Now, after we finished these 3 questions, let's do a quick summary. When we receive the question, we first need to identify what is the type of this backtracking question. Then we need to think of how we're going to implement backtracking to solve this question. Then we can simply go to the formula, choose the right parameters for our recursive function. We need to think of a base case, create logic and a recursive call that will make us go towards the base case, and then we need to backtrack. So there you have it. This was my backtracking video. Please let me know in the comments if you enjoyed the video or what topics do you want me to cover next, and I'll see you on the next one.